So our idea of a mathematical argument is it's basically these exact sentences that I wrote, except we don't really make the reader stop and say okay and stop and enter a number. We just want to use the words from our end, from the author's end, as our argument. And then the reader can decide if he or she would like to stop and pause and fill in and read through the proof that way. But the mathematical argument itself are just the words in this explanation. So this is the way that it actually looks in the book. Again, we write it as a letter to this person, the reader, who is skeptically looking for a counterexample to the statement. You can see all the phases of what I talked about. I start off, thinking of any example satisfying the hypothesis. I'm saying what I know about that as because of it satisfying the hypothesis. Then I'm turning my attention to the conclusion here. I know the conclusion has to do with the value of n minus 1, and so that's what I'm addressing here. And then finally here, I'm summing up why the work that I've done before there is demonstrating the conclusion of the statement. In other words, the stuff I have here is demonstrating that n minus 1 is not prime. So that's just an explanation based on what the word prime means. So our proofs always are going to have these four phases. And I would capture them this way. Let me back up here, and since I have a little bit of room on this slide, let me get rid of this. Let me just try to describe what each of those four phases are, and these really are the four phases in any direct proof. Phase 1 is to say let an example satisfying the hypothesis be given. Okay, so this is me saying to the reader, I know that you are picking examples satisfying the hypothesis. So I'm just saying, so write down an example satisfying the hypothesis. Give an example. You're not asking for a response. You're just saying, you write down an example, and you would want to give letters here to the parts of the example so that you can refer back to them. Second phase is you're going to explain what you know about this based only on the fact that it satisfies the hypothesis. So in the previous example, we know that the hypothesis was that the number that was written down as a perfect square. The only thing I know about perfect squares is that the number is something squared. So that's all that I wrote down for step 2. Step 2 can get kind of long if you actually have built up a large body of knowledge about something. It may be that when the reader picks an example satisfying something, you have lots of things that you know about it, and you'll have to decide which things are relevant and which things are not. But in these simple proofs that we start with, there's not going to be too much that we can do. We're not going to get too far away from definitions in step 2. So step 2 could be way more than one sentence. Step 3 is basically to turn our attention to the conclusion. So I'll just say, consider the conclusion. So in the previous example, this is when I stopped talking about n being a perfect square, and I started talking about n minus 1 and how it might be written as a product, because we were trying to conclude something about n minus 1 being prime or not prime. So I was thinking of what do I know about n minus 1 relative to it being a product of two numbers. And then step 4 is really just explaining, I'm going to explain why what I did in 3 shows the conclusion is true. So the work I do in 3 should be building a case for the conclusion being true, and then in step 4 you want to explicitly say why what you've done till now actually shows the conclusion is true. So overall, what this means is that in this process that the reader is going through of picking examples satisfying the hypothesis and then checking the conclusion, what we're showing them is that no matter what they pick satisfying the hypothesis, their example will never make the conclusion false. And so in other words, no matter how hard they try, they will never find a counterexample to this statement. Okay, so let's get back to Oh, I guess I should say that when we, as we go through this course, we do start off writing proofs in this very long, prose style, but we pretty quickly want to not do that. We don't want to have to write that much in order to be able to convey an argument. So we really prefer, ultimately, to end up with a terse version of the same thing. So here's what the terse version would look like. But I want you to see that it has exactly the same components. We talk about the proof starts, let a perfect square n be given. That is just telling saying to the reader, write down an example that satisfies the hypothesis. Then we say what we know about it. There's phase 2. The second sentence is exactly what we know about the example that the reader picked based on the words that were in the hypothesis. Then you can actually see, in this case, it's sort of a transition form, but I'm turning my attention to n-1. I'm turning my attention to the conclusion. Right? The hypothesis doesn't say anything about n-1, the conclusion does. So here I'm turning my attention to the conclusion, and I'm writing down what I know about n-1, because the conclusion is about n-1. Now I am using here the fact that I know that I have to do something about primes, and so I'm trying to think about how n-1 might factor, might be written as a product. So I do have some idea of what I'm trying to accomplish here. And then once I see that, I say, oh, I have actually written n-1 as a product. And so step 4, phase 4, would be to say why what I did in phase 3 actually shows that the conclusion is true. And so here's the conclusion, and I'm wrapping it up with the conclusion. Notice that the hypothesis is here, and that's how I'm starting. Right? So that's going to be the structure of my direct proofs. Now let's try it with some simpler statements, because we don't want to have to be too clever too quickly here. So here's a statement about odd numbers. If the number is odd, then so is its square. In order to be able to prove that, I'll need to decide what it means to be odd. I have to make sure that the reader and the author agree on the meaning of n is odd, that predicate. I don't think I left myself a slide for that, so let me see if I can open one. All right. So I'll start with even. Even's a little bit easier to define than odd. N is even if n is a multiple of 2. That's how I want to define it. So I'll say n is twice something, and I'll say for some integer k. So it's important that we say that the number here that we're twice is a whole number, otherwise it's not a meaningful definition. Everything is twice something, right? 5 is twice 2.5, so it doesn't make 5 even. So the thing that makes n even is being twice a whole number. So it is important that we actually say that it's twice k, where k is a whole number. We'd like our definition of odd to be sort of like this. We don't want to say n is odd if it's not even. We don't want to give a negative definition. We like to give a nice positive statement. So the positive statement for being odd, that's very similar to the one for being even, is this: n is odd if n is 1 more than a multiple of 2. And so for some integer k, same business. So this gives us a nice symmetry between the definition of even and odd. It distinguishes between them. It's not the way we normally think of even and odd. If someone just gives us a number, and asks, is 203 even or odd? We don't really think of it this way. But for the purposes of our proofs, this really is the simplest way to define even and odd. So let's get back to our proof at hand. Remember 4 phases. One is to say, let an example be given that satisfies the hypothesis. So I would say, let an odd number, I'm going to abbreviate here, it's hard to write, n be given. And I would ask you not to abbreviate too much when you write. I really want to see complete sentences. I don't abbreviate when I'm writing on paper. I just have a hard time with the tablet. So phase 1 is, give me an example satisfying the hypothesis. Step 2 should be, what is it that I know about n? So I can even say it that way. I can say, I know n is equal to twice something plus 1. for some, and I'll abbreviate this as well with math symbols, I can say for some k in the set of integers. So that's another way of saying the statement that I wrote before, this statement, when I said for some integer k, another way of saying that is for some k in the set of integers. This z is set of integers. Now I'm going to turn my attention to the conclusion. That's my step 3. So I'll say hence, and the conclusion is about n squared. So I should be now talking about n squared. Well, what do I know about n squared? Not much. All I know about n is that it can be written as 2k plus 1, so I'll use that. If n can be written as 2k plus 1, then n squared is 2k plus 1 squared. I can use FOIL to multiply this out. Take a second to do that. You should get 4k squared plus 4k plus 1. And that all seems fine, but it doesn't seem like it's going anywhere. You might have to go back and remind yourself what you're trying to show about n squared. We're trying to show that n squared is odd. Well, remember, odd means that the expression for n squared could be written as 2 times something plus 1, right? That's what we decided that odd was going to mean. And so in order to show that n squared is odd, I'll want to show that n squared can be written as twice something plus 1. Well, algebraically, I can make these last two things match if I put in the parentheses here 2k squared, and I'm just putting in what needs to be there to make these equal, plus 2k. So within the parentheses 2k squared plus 2k, now these last two statements, or last two expressions, this guy and this guy, are equal. Okay? So that's a weird thing to do algebraically. I admit it. It's not simplifying the expression or factoring the expression. It's just rewriting it in an equivalent way. But it does show, moving on to phase 4, because that stuff in parentheses, so since that stuff in parentheses, the 2k squared plus 2k, is an integer, the stuff in parentheses there is a whole number. And the reason I know that it's a whole number is because I know that the whole numbers are closed under multiplication, addition, and subtraction. So if you start off with an integer k, which we do, and of course 2 is an integer, so 2 times k plus 2 times k, that's just using multiplication and addition with integers. And so I know the result of that will be an integer. So the stuff in parentheses is an integer, and so the line before, the thing I did in step 3, really does show that n squared is twice an integer plus 1. In other words, n squared is odd. So I'll say, because the thing in parentheses is definitely a whole number, this shows that n squared is odd.